Okay, Assalamu alaikum, inshallah. Welcome back to the class. I wish you had a good weekend. This week, we are going to have the quiz, the last quiz. This last quiz is going to be on Tuesday, and it will cover the power screw. Also, I would like to tell you that I already finished grading the last quiz number 5. I couldn't honestly do it the same way I did it before, which is marking the quiz. So if you have any inquiry about why did you get the mark that you got, then please just send me an email and I will explain it to you, or you can meet with me during the office hour and I can explain this to you. There was only one student who answered the quiz correctly, but the solution has something wrong, and it was I think it was a coincidence that he got it right. So instead of getting 10, he lost a few marks. If you are that student, you are most welcome to come and talk to me. The rest, whatever you see, is now your mark, okay? That's it, I think. Today, we are gonna cover as you see in the title, bolted and riveted joint loaded in shear. So if you think about it, what we did in the previous part of this chapter was to look for bolted joint under tension, whether it is fatigue or which is cyclic loading or static loading. And that was tension, under tension. The title was very clear. It was under tension. So this time, we are going to talk about shear, okay? And it is very interesting, very focused sections, but you need to be very careful in the sense that, for example, what you see here is a diagram that you are familiar with from the civil engineering course that you took, which is showing you some rivets joint, and they are subjected to a shear loading. This is one of the simplest loading that you covered when you were doing CE 203 or CE 203. So, but what we want to show you here is that for the most part, the shear, is like F over A, except that F is a shear force and that area is a shear area. There are some details that may make this relation F over A a little bit tricky, so you need to focus on over here, okay? So what do we have here? We have a riveted joint. This is A, and for A, says that this is a shear loading. And as you see, the rivet is right there, okay, with two heads like this to prevent the plates from moving in the transverse direction, and the loading is acting in this way. Rivets are very important. You may not appreciate them much because you think that you don't see them often, and I don't blame you, because these guys are hidden within the structure of airplanes. They are very important for airplanes, and there are some other applications, of course, where rivets are used. So what happened that we can have different situations. Like, for example, if the rivet happened to be stronger than the material itself, then by doing that loading, okay, which is a shear loading, what happened? If you think about it, this force is shifted a little bit from the center, and this force is shifted a little bit from the center. So if you think about it, this is like this, right? Or the same way, it is like this. Now, we know that if you have this kind of couple, then you will generate a moment. Now, but here we're not talking about the mechanics of forces. We're talking about the mechanics of the material itself. What happened to the material? So if the rivet is strong, but the material is weak, the material will tend to deform in a kind of rotational way due to that moment. So what happened? This bending that you see, bending always produces this curvature, right? So this bending that you see is because the member themselves started to lose their strength. They started to deform due to that moment. Now, the other situation is that the member themselves are very strong or strong enough not to bend because of this moment. They will not bend, but rather the rivet is weak and thus we shear it off. This is when we cut the rivet, we shear it. So this is another situation. Now, the other situation is that, look, the member might be strong, maybe thick enough, or the combination somehow ended up having the rivet safe, and the member themselves, which are these two members, the one on the top, the one on the bottom, and instead of like bending, they fail. Why? Because with respect to the member, there are two holes, okay, which is enough to create stress, okay? And for some reason, we told you, if you remember, that we don't consider, stress concentration when we analyze static loading, because we think that materials for machines are strain hardening material. That's what we did. And we told you that because we are operating mostly within the elastic region, so if the stress here get higher than the stress here, it may reach to yielding or around it, and that way material will be okay. It's actually going to get harder. But if you continue the loading, that stress will end up reaching the ultimate, while the stress here might reach yielding, and that's why you get failure of the member. Now, there is other situation where the member is not going to fail like break, but rather, which is E, this is bearing of the rivet, okay, on the member, or bearing of the member. So what happened? The bearing stress, which is the stress resulting because of an area pushing against another one. So if you think about it, this rivet has a projected area, right? It is circular, but it has a projected area over there. And this projected area might push against the member. The member also has a projected area, shabab. Is that true? So what will happen if you look at this? The projected area of the member is this one. So if the situation happened because of bearing stress exceeding the limit, then you will see that the members start to crumble, just because of that area pushing from the rivet, pushing against the member. There is another mode of failure, which is called the tearing out. What does it mean? You can easily do this by having a very strong rivet made, for example, from metal, and then you have a plate, okay, clamped by that rivet, and this plate, ya shabab, is maybe made up of a softer material. And thus, when you pull, what happened? The rivet itself will cut through the material. كأنه سكين شباب. From both sides, it will shear it off. The third one, this 1, 2, 3, 4, 5, 6, 7. The seventh one is what is called the tensile tearing, or the tensile tearing means that what will happen due to the fact that the rivet is maybe close to the edge and having a huge, there a significant plastic deformation ahead, then this area, will become weaker. There is an area in front of this, just like an area of stress concentration. And because there is no material in the end, that part become highly deformed, and it may reach to the ultimate or failure stress, and that's why you have a tearing. Now, if you think about it, most of these are, relation somehow F over A. There is always F over A. But you will see, except for the edge tearing, which we will talk about it later, it has a little bit different relation. But most of the time, we will see that this is what we are going to do. The only thing is, for example, يا شباب, you want to make some distinction. If the rivet is like this, and you have a plate, which is one plate riveted, with another plate. Let's just assume, just for the assumption. Now, I intentionally made these two plates, one of them red, one of them is blue. They are different and they have different thicknesses. So you want to be careful when you analyze it. This is just a hypothetical example. And the idea here is that you would want, for example, if you have the shear forces, to check what happened to this one, what happened to this one. Of course, you will not be deceived by the fact that, the blue one is safe because it's thicker, while the red one, no. Maybe these are made from different materials, maybe not. So you need to be very careful. The relation is not very difficult, but you need to be very careful. So the bending stress in the member, which I told you about, due to the couple, is related to just, sigma. It's going to generate stress, which is sigma equals to M over I divided by C. C is here on the top. And F is basically the force multiplied by the thickness, divided by 2. So there is also the shearing force, which can act, on for example, if you look at the rivet is circular, and if there is a shearing force acting on it, then the shear area is this. That's the shear area, right? So you want to know, for example, speaking about the shearing area, this is a riveted joint. And with the riveted joint, we know that rivets are made from this nice, smooth, usually aluminum cylinder with 2 caps on top and on the bottom. So it doesn't actually matter where do you shear it. Is it here or is it here? It doesn't matter. You will end up always having the same area. But we will today introduce you to another concept of bolted, joint under shear. Now, with bolted joint under shear, for example, if I tell you that this is let me do it this way. If this is one member, and then there is another one, and what happened is this: the bolt with hexagonal nut and washer and everything is now going like this. This is the nut. These are the extra thread. And let's say you calculated L, you calculated LT, and then you calculated LD, and then you calculated small lt, and you discovered that the thread is going all the way to here. And then I told you that there is a shear force like that. Do you see this? Now, my question to you, if I say that this is the shear force and tau equals to F over A, what is the area here? What is it? Anyone يا شباب؟ Nobody's paying attention.
No, we are paying attention, but
يا شباب, guess. We have a few areas. Guess one. Is it AD? Is it AT? Is it AR? Do you know all of these areas? What is the difference?
Yes, AD is the major diameter.
AD
area
is what? Is the area here? This is AD.
Yes.
What is AT?
It's an approximate area that determined by.
Yeah, it is an area of the threaded part. But
Yes.
what is there? Somehow an average area.
Yes.
طيب, what is AR? AR يا شباب is the root area. The area of the root, if there are two threads opposite
The
to each
minimum
other,
area.
this distance from here to there is called AR, because I mean the area here, because this distance is DR and the root area is tabulated just like the tensile stress area. So we will show you later that the decision about which area here is very important, because you will not know which one. Maybe with respect to you, the difference is not too much, and the factor of safety instead of 2, it will become 1.8. But it reflects that you don't understand, and this is the problem with this kind of questions. So the other area is the tensile area. So if you have F over A and there is a load, and like for example, if the member يا شباب, while you are pulling the riveted joint, this is the rivet, and you have a force over here, and if you want to check if the member is going to yield here, okay, then basically you will take this area, okay? So this is F over A, and this is the normal stress. You understand? The other one is the bearing stress. Now, the bearing stress, if you remember, we said it's always negative because it is an area pushing against another area. And in that case, you will always think that, okay, what is the diameter here of the rivet? And then what is the thickness over here? So for example, if you think about one plate, you would say this is the thickness of the plate. Then the projected area which is causing the bearing is actually only the diameter of the rivet multiplied by its thickness. That's the area. That's the bearing area. And the stress, the bearing stress, will become minus F over A, and this A is the bearing area. Do you understand? We will have an example about this. So what are we gonna do? We're gonna talk about this example. I don't know. I think this example has been removed from your textbook. I don't know why. Maybe because it was a little bit confusing. And the reason why it was confusing is because what happened here is this. Let me explain to you this problem. Okay. So basically, what do we have here? We have cold drawn. So this one is cold drawn steel 1018. Okay. And this one is also cold drawn 1018 cold drawn steel. They are made with different colors just to tell you that there are layering, okay? Which is this one are one plate, and this one, okay, and this one where I put the two dots, they are two different plates. This plate has a thickness of 1 inch, while this one and this one, each one has a thickness of 1/2 inch. Okay, what we know is that the bolt used over here, the bolt used, so this is a threaded bolt, it is not a rivet. Okay, 3/4, this is the diameter, 16 UNF, 16 is in the number of thread per inch. This one is a fine threading, and SAE grade 5 will let you know what is SP, what is SE, and so on. Of course, we don't need SE here. We just need SP, or maybe even the yield stress or something. Why? Because the problem is static, it's not fatigue. Okay. So what happened is this. As you see, let me clean this up. We have a load in. What happened, ya shabab, is this. This F will pull from this side. The bolts are coming through, and because of this, the load is transferred to the other slices. Okay. Now, from the top view, we can see that we have actually 4 bolts. Okay, 4 bolts. So what are we going to do is this. If you look, and I think this is why this problem is confusing. Yani, this is why maybe they removed it. It was confusing everybody. What happened is this. If you look at this, the thickness of this one plus the thickness of this one is 1 inch, which is similar to this, right? So with respect to bearing stress and other, and not only this, if you look at shearing, that force will be transferred to this, and this, like that. So the bolts will take the load equally, okay? And the slices will also share the same, the load in like half of the load up, half of the load down. But if you think about them together as one piece, or you think about the gray one as one piece, you are having the same thickness. And thus, this is why in this problem, the solution is only focused on the gray one, because it is not different than the top one. You may argue, ya shabab, that but the top one has a thickness only of 1/2 inch, while this one has a thickness of 1 inch. Well, انت امامك خيارين يا شباب. No third one. Okay, either to analyze the 1 inch alone, or analyze the 1/2 inches, 2 of them together. And when you put them together, their thicknesses will become 1, and خلصنا, صار نفس الشيء. Do you understand? Also, what add to the solution why it's like that? Because with respect to material, they are not different. And thus, I don't need to worry. You understand? So I hope you understand this very well. Now, if this is the case, then what are we going to do? We are going to blindly think about the gray one, Okay, and look, the gray one, if you look at this one is separated from here. Look, it's one piece by itself. So the gray one is actually like this, with a thickness of 1 inch, okay, a width of 4 inches, and there are 2 bolts. So that force over here is going to be equal to F over 2 here and F over 2 here. So each bolt will take F over 2. That's it. That's it. That's a problem. Now, what do you need to look for is this. Let me maybe I'm not gonna erase this. I'm gonna show you just something very important. What you need to think about this distance. This is how much? It is 1.5 inch, 1.5 inch, and the diameter of the bolt is how much? Is 0.75, right? Is that true? It is 0.75. So why I'm asking you to do this? Because in one of the solutions that we are going to do, we will need to know what is this distance. Why? Because the edge shearing, you will see there is an equation for it, which is a function of how far is the bolt is from the edge. And I think, يا شباب, you agree with me that this is very intuitive. Intuitive يعني معناها إنه شعوريا we can feel it. Is that if you have a blade, just think about a blade, and you put the bolt in the edge, or you have another blade, and then you put the bolt in the middle, and you fix the bolt, you hold the bolt, and then you apply the load. Which one do you think is more risky? Yeah, this one, because the one at the edge, because there is a good chance that you will shear off this little ligament, little piece of the material much easier. So that's why I am telling you about these dimensions. Okay, now what does it say? It says that we want to design for a factor of 1.5 and to determine the static load F. احنا الآن مشكلتنا شنو؟ نبقى نعرف how much is F. Now this problem, okay, is tricky because the question itself says, what is the loading capacity? But this is the real life. This problem is similar to real life. يجي واحد ويقول لك أنا عندي هالمشكلة هذه، يلا حلها. كم مفروض أحط F? How much is F without getting failure? Now you will be, you'll be now responsible for figuring out what kind of failures can happen. And these failures, how can I treat them mathematically? How can I convert them? احنا ايش قلنا مثلا ممكن يكون في bending، ممكن يكون في bearing، ممكن يكون في shearing، ممكن يكون في edge shearing، ممكن يكون في yielding. تخيلوا يا شباب, nobody is going to teach you this. You need to figure it out. You need to figure out all kind of possibilities, convert them into equation. These equation has a factor of safety and F, and then find F. Now, what are the expectations? What are the expectations? The expectations are like this. You will find F, which is equals to 5. You will find F, which is equals to 10. You will find F equals to 2. You will find F equals to 1. Why? Because the material will be stronger in one mode of failure than the another one. And thus, it will let you, if it is strong, it will tell you, go, you can go apply a big force. But if the material with respect to that mode of failure is weak, it will tell you, no, don't apply a lot of load. And thus, you will go and say, okay, I have like 5 loads, and I will pick the lowest. Why the lowest? It's very simple. Because you need to secure the joint from all kind of failures. And that's what we are going to do. Okay? All right. So the first thing is this. What are we going to do? We are, طبعا يا شباب, this is the explanation I told you about, that the slices will take half of the load and they have the double the thickness is equals to 1, and that's why we are. The first mode of failure is bearing in the bolt. What does that mean? It means that I will assume that when this is the blade, okay, I cut it into half, and this is the bolt over here, and the blade has a thickness. Now, what I am assuming over here is that the projected area, which is the projected area? If you look at the plate from the top, you will see that you have this and this, the places where the bolts are. The projected area is simply this diameter multiplied by the thickness. So if this is the projected area, is going to be like this. Of course, this is like this is like that. And I need to erase this just not to confuse you. Okay, so what happened? The projected area is this area, which is a rectangle. Okay, and this rectangle as a bearing area is pushing against the rivet, the bolt. Why? Because I can do the opposite. I can look at the bearing stress on the member, not on the rivet. So in general يا شباب, what is going to be the stress? أول حاجة احنا قلنا بأنه الفورس على البولت الواحد هي F over 2. هذا أول حاجة. So if I have a stress, it is equal to F over 2, and then the area, it is F over 2, and then the area A. Now, the question is, what is this area? And not only this, in order to find the force, I need to equate this with what? With an allowable stress. The allowable stress is equal to the strength. وأنا قاعد أتكلم عن البولت strength حقه SB. And then I divide SB by what يا شباب? By a factor of safety. ND. You see that? Now, so what happened over here? And now I need to go and look for the area. The area is not very difficult. It is the thickness multiplied by the diameter. That's the area. So if I solve for F, I need to multiply 2 by A by SB and then divide by N, which is this equation, right? And then what do I do? Look, the 2 is a constant. The thickness is 1. We agreed that is 1. And then the diameter of the bolt. The diameter is the diameter of the bolt, which is a 3 over 4, because the hole has a diameter of the bolt. And then 85 is the proof strength for SAE grade 5 divided by the factor of safety. How much can I apply? 85 kilo-pound. Not kbsi, it's a force. It's a kilo-pound. Okay, now I go to the next one. What if I look at the member, not the bolt? ممكن البيرنج يصير للممبر. Exactly the same equation, except that the strength here is the yield stress of the member. ما معقول أنا أتكلم عن الممبر وأحط له proof strength. ما معقول يا شباب. Doesn't make sense. So it's exactly the same equation. This is 2. This is 1, the thickness. This is the diameter 3 over 4. And this is 54, which is the yield stress of the material. The yield stress of the material turns out to be 54, while the proof strength of the bolt is 85. So what happened? You got a lower force. Now you are afraid that the member will fail, not the bolt. The bolt is too safe. It's too safe. You can apply up to how much? Up to 85 kilopound without failing the bolt. But here you can apply up to 54, and then after that, the member will start failing. Now, the next part is this. We will look at the shear of the bolt. The bolt is being sheared off. The member will not be sheared off, but the bolt is. So what happened is this. The shear of the bolt, okay, is the following. If the bolt thread does not extend into the shear plane, what are we talking about over here? Is that we are assuming that the shearing is happening in the shank area. So this is the thread. The thread might be here, okay? But the shearing is happening right there. So if it is happening right there, we have the area equals to pi over 4d squared. But if the thread goes all the way, لأنه يا شباب the plate, okay, well, one of them is moving right, the other one is moving to the left, and the shearing we need to know. Now look, this part will probably, this shearing part will probably be in the shank. The problem with this one down, there is a good chance that this is in the shank. There is a good chance that it is, actually, there is a good chance it's in the thread, not in the shank. So, if there are no details given, of course, طبعا يا شباب, in the exam, you will probably not solve both of them. You will go find the length of the grip, all of it, yeah, and then add to it the height of the knot, and add to it at least 2 threads, and then find LT, and then find LD, and then find LT, the small LT. Okay, and you will know exactly what is this. Sorry, ya shabab. You will know exactly what is this. Is this area is in the thread or not? Now, what are the consequences? The following, ya shabab, is that here, look, the first thing, أول حاجة إن allowable stress tau allowable is what? Tau yield divided by ND. Now, what is tau yield? Shearing is happening on the bolt. So, tau yield will be equals to 0.577 SP. ليه؟ لأنه ال SP is a normal property of the bolt. And if we multiply it by 0.577, this magical number is going to transform SP into a shear proof strength. Do you understand? And that's why we multiply 0.577 by SP divided by ND. Good? So,
Good.
what happened? Yes?
Yes, I said good.
Okay. Now, this is the idea. There is one little thing which is different over here. You need to be careful about. Okay? Is the fact that the area is pi over 4. So this is pi over 4d square. This is pi over 4d square. صح ولا لا? Is that true? From
Yes.
where did we get the 4 over here?
Is it because we take one side of the sheared bolt? We have 4 sides.
Because, ya shabab, the shearing is happening here. The shearing is happening right there. Do you get that? So in here, this part is where the shearing is dangerous. And this part is one plate. You see that? And this one plate has how many bolts? 4. That's why we divide by 4. Do you understand that? The shearing is not going to happen, ya shabab. Is not going to happen because this one, the gray one, will cause bearing, yes. And with respect to bearing, you look at the 2 pinks or the gray is the same. And we said that with respect to the bearing, if we look at the gray one, we will have the force divided by the 2 bolts. But the bottom one is where the shearing is going to happen. And the force is going to be transferred, F. The force is going to be transferred to the 2 slices. Do you understand that? I hope you do. You can think of it this way also. If you look at the problem, you see that we have this force, okay? And if you just look at it and you cut this, okay? Let's cut this. This is how we draw a free body diagram. So I don't want you to look at this anymore. Now, if you look at this one, okay, what would you see? You would see that this force is going to be transferred into what? F over 2 and F over 2. Is that right? صح ولا لا يا شباب? Maybe it wasn't a good idea to put too much. Let me put it this way. And then let me make this one gray. So what happened is that this F, okay, is going to be transformed into F over 2 and F over 2. If you look at the slice in the bottom, F over 2 with one slice, this slice is small, its thickness is 1 over 2, and it has how many? 2 bolts. So you have F over 2 here, and the bolt, each one will take half of it. So this one is F over 2 divided by 2. So what will happen? It will become 1/4. And this one is F over 2, and then you divide it by 2, okay? And you will end up with F over 4. So the half, you will divide it by 2, and it will become F over 4. And that's why here we have F over 4. Now, to save the time before the class finish, we do this twice in here, just to show you the exercise. One time, ya shabab, we use the area as the shank area. So the area of the bolt as pi over 4 d square. What is d square? It's 0.75, 3 over 4. The next time we look into the what? The thread. If we use the thread, then the area is AR. Exactly the same equation, but the area become AR. And look, while here, you will be allowed to apply 57.8 kilopound, with AR, you got how much, ya shabab? 45. That's a lot. That's a lot of difference, just by considering the root area. That's why it is very dangerous. You need to think about the root area. Now, the last part, two parts يا شباب is this, the edge shearing, and the edge shearing, look, it is tau, which is equal to F over 4 AT. F over 4, because يا أخوان, we will think about the division of the forces over 4. And then we have AT. What is AT? I will tell you what is AT. And then what is going to shear? When we say edge shearing, it is the member. So we convert the yield stress of the member into what? Into a shear stress by multiplying it by 0.577 divided by MD. Now, what is A? A is this, ya shabab. You see? It is the distance from here all the way to the end. So you need to go and figure out how much is the distance from the diameter of the bolt to the edge, and you substitute this A, and then you can find F. F for edge shearing is 93.5. So it is very, very safe. There is no worry about it. The last thing that we need to think about is the yielding of the member. Now, with respect to yielding of the member, you need just to think about one thing. The member has two cuts. So the area is this, wait, is going to be what, ya shabab? It's going to be this area, and this area. So to find these areas, what do? You go and calculate all of this, and you subtract from it twice as the diameter. So if you remember, the area is the thickness of the blade is 4 inches. Then you subtract twice as the 3 over 4. And then you got the resultant area. You multiply it by the thickness, and then you deal with it as an allowable stress, which is equal to the yield stress of the member, 1018, called drawn, divided by the factor of safety, and then you end up getting how much? 90 kilopounds. So what is the last one is, what is it? This one is this is the yielding across the bolt. You may also get yielding in here. Do you see that? How about this part? This part is very simple, ya shabab. The area is the width by the thickness. Okay, and how much did you get? 114. طبعا يا شباب, it's very reasonable, right? If this one got you 90 with the cut, this one will be higher because there is no cut. Okay, and now if you look back, you will see that the most dangerous load is this one. So you will decide to use the lowest one. Okay, I reached the end of this. We'll try to give you a summary next class, and then we'll talk about the shearing with a moment. Okay, now I'm gonna ask you to switch on your webcams and take the attendance, ya shabab. Okay, Faisal? Faisal? Bushal? Yusuf?
Here.
Hamad?
Yes.
Qahtani Ali?
Yes.
Yusuf اليوسف?
Yes.
ماجد عباد؟
Yes.
حسين العلي؟
Yes.
محمد؟
Yes.
العياش؟
Yes. Yes, here. دكتور.
دكتور ما نسمع صوتك. دكتور ما في صوت.
يا شباب تسمعون صوت الدكتور؟
لا والله ما نسمع
لا
شيء.
لا ما نسمع. مشكلة ما ندري الحين نطلع ولا كيف.
لا الدكتور كان موجود.
يا شباب, can you hear me?
Yes.
Yes, doctor. We can.
Okay, I'm very sorry I got disconnected. العياش, are you here?
Yes, I'm here.
دوسري مبارك
Yes, here.
and أحمد غزالي.
موجود يا دكتور هنا.
الحاجي علي is here.
معجب.
معجب. سلطان الحربي.
موجود يا دكتور.
سلطان I can see you. الحجاب عبد الله.
Yes.
سلطان الهوشان.
Yes.
عبد الرحمن.
Yes.
خالد العتيبي. خالد. عبد الله العوفي.
Yes.
فارس قحطاني.
Yes.
فارس. ثابت القحطاني.
Yes.
زهير. علي رمضان.
Yes, doctor.
هشام.
Yes.
هاشم.
Yes.
ماجد. ماجد is here. محمد.
Yes, دكتور.
أحمد. سلطان.
Yes, doctor.
مشعل يامي.
Yes, doctor.
وليد.
Yes.
محمد.
Yes, doctor. موجود.
and so Sufyan is left. سنبل أحمد.
Yes, doctor.
okay, so that's it يا شباب. أبو شهل, are you here?